Hello friends, so welcome to engineering tutorial. So today we are going to solve some numericals on specific heat, heat capacity and calorimetry related to that. So this is the first question related to specific heat, heat capacity and calorimetry. So it is given that a sphere of aluminium of mass 0.047 kg is placed for sufficient time in a vessel of boiling water so that the sphere is at 100 degrees Celsius. It is then immediately transferred to a 0.14 kg copper calorimeter containing 0.25 kg of water at 20 degrees Celsius. The temperature of the water rises and attains a steady state of 23 degree Celsius. Okay, so calculate the specific heat of aluminium. It is given the specific heat of water is 4.18 into 10 to the power 3 joule per kg per Kelvin. Specific heat of copper is 0.386 into 10 to the power 3 joule per kg per Kelvin. Okay, so this question is based on the principle of calorimetry, specific heat, and the concept of heat loss and heat gain, okay, in a calorimeter. So let's say this is the aluminium sphere and this is the copper calorimeter. So the aluminium sphere, it is at an initial temperature of how much? 100 degrees Celsius, because it is dipped for enough time in boiling water. And this is the copper calorimeter, which is filled with water. The mass of the aluminium sphere, that is equal to 0.047 kg. Mass of the copper calorimeter, that is equal to how much? 0.14 kg. And the mass of water in the calorimeter, that is equal to 0.25 kg. So the copper calorimeter and water, initially it is at a temperature of 20 degrees Celsius, and the aluminium sphere, initially it is at a temperature of 100 degrees Celsius. So the aluminium sphere, it is, we can say this is the hot body, and this water and calorimeter combination, that is the cold body, because it is at a lower temperature, that's why I am using this term. So when this sphere is put in the calorimeter, obviously there will be loss of heat energy from this aluminium sphere, and heat energy will be gained by the water and copper calorimeter combination. So the temperature of this aluminium sphere, it will drop, and the temperature of water and copper calorimeter combination, it will increase from 20 degrees Celsius. So they will arrive at a common equilibrium temperature, which is how much? The final equilibrium temperature, the steady state temperature, that is equal to 23 degrees Celsius. So aluminium will lose heat energy, and copper calorimeter and water, it will gain energy. So according to the principle of calorimeter and this whole thing, heat lost by the hot body is equal to the heat gained by the cold body, thus arriving at a final equilibrium temperature. This is the basic principle. Now we have to just put all the numbers together in the formula and get the result. So this is the basic principle. So now for the aluminum sphere, okay, fall in temperature delta T is equal to final minus the initial. So actually it will be in a way it will be Ti minus Tf. It is negative, isn't it? Tf minus Ti, because the final is 23 degrees Celsius and the initial it was how much? 100 degrees Celsius. So it is minus 77 degrees Celsius. This. So the magnitude of heat loss, the negative sign indicates that it has lost heat. The negative sign, it indicates that it has lost heat. But if we have to calculate the magnitude, it will be the magnitude of heat loss be equal to mc delta T. So the mass of the aluminum sphere, that is equal to 0.047, then the specific heat of copper which we have to calculate, and the change in temperature. Here we will use 77 degrees Celsius, only the magnitude. Okay, so this is the loss of heat by the aluminum sphere. This is very important. Okay, so this is the thing. So here one interesting thing you should notice, that the information related to specific heat, it is given in terms of joule per kg per Kelvin, but the temperatures they are given in degree Celsius. So here one thing you should know, one interesting thing is that, see, here let's say we do a simple thing. First, the interconversion between Kelvin and Celsius. The temperature in Kelvin is the temperature in Celsius plus 273.15. Okay, that gives us the Kelvin temperature. 0 degrees Celsius is 273.15 Kelvin. Similarly, 1 degree Celsius, it is equal to the Celsius temperature plus 273.15. So it will be 274.15 Kelvin. So here pay attention. Let's say we calculate the difference, 1 degree Celsius minus 0 degrees Celsius. So it will be the same as 274.15 Kelvin minus 273.15 Kelvin. So 1 degree Celsius, a difference of 1 degree Celsius, not 1 degree Celsius, a difference of 1 degree Celsius is the same as a temperature difference of 1 Kelvin. Okay, so let me again highlight it, that a temperature difference, increase or decrease in degrees Celsius, is the same, numerically it is the same as the temperature difference in Kelvin. Okay, an increase or decrease of, in let's say 1 degree Celsius, is the same as an increase or decrease by 1 Kelvin. So here When we say that the temperature fell by 77 degrees Celsius, it also means that the temperature fell by 77 or minus 77 Kelvin. Why? Let us calculate. 23 degrees Celsius will be equal to how much? 23 plus 273.15, which will be equal to how much? 296.15 Kelvin. Then 100 degrees Celsius is equal to 100 plus 273.15, which is equal to 373.15 Kelvin. So here if we calculate 100 degrees Celsius minus 23 degrees Celsius, that is equal to how much? 77 degrees Celsius. Same if we calculate the equivalent Kelvin temperatures, that is 373.15 Kelvin minus 296.15 Kelvin, that is equal to how much? Okay, 373.15 73.15 minus 296.15, also 77 Kelvin. Same result. Both ways they are the same. Okay, but here you have to pay attention that it is an increase or decrease of temperature, not a specific temperature. It doesn't mean that 1 degree Celsius is same as 1 Kelvin. No, 1 degree specific temperature of 1 degree Celsius is not equal to 1 Kelvin, but an increase of 1 degree Celsius from a specified temperature is the same as the increase by 1 Kelvin. So increase of 1 degree Celsius also means that there will be increase in 1 Kelvin. A decrease of 1 degree Celsius is same as a decrease in 1 Kelvin. So that's why directly we used the temperature difference of 77. Okay, so that is very important to understand. So from now on, mostly we will be dealing with Kelvin and Celsius. Okay, so directly we'll use the temperature difference in Celsius. So this is heat lost by the copper. Now for the copper calorimeter and water combination, okay, so the mass of water which is present, it is equal to 0.25 kg. Okay, the mass of the copper calorimeter, that is equal to 0.14 kg. Both they were at an initial temperature of how much? 20 degrees Celsius, and then the equilibrium temperature, the final equilibrium temperature, that is equal to 23 degrees Celsius. So here there is a rise in temperature. So the difference of temperature is equal to 23 degrees Celsius minus 20 degrees Celsius is equal to plus 3 degrees Celsius, or which is the same as plus 3 Kelvin. Okay, this much. So here specific heat of water, that is equal to 4.18 into 10 to the power 3 joule per kg per Kelvin, and specific heat of copper is equal to 0.386 into 10 to the power 3 joule per kg per Kelvin. So for both the water and copper calorimeter, the heat gain is equal to, for heat gain will be for both the water and copper calorimeter separately. So it will be MW CW delta T plus MCU CCU delta T. MW is mass of water, CW specific heat of water, delta T is the rise in temperature, that is 3 degrees Celsius or 3 Kelvin. This is MCU is mass of copper, CCU is specific heat of copper, delta T is same rise in temperature. So it is equal to, the rise in temperature is the same for both the cases. So we can write it as MW CW plus MCU CCU into delta T. So it is equal to 0.25 into 4.18 into 10 to the power 3 plus 0.14 plus 0.386 into 10 to the power 3 into 3 Kelvin, because everything is Kelvin, the same as 3 degrees Celsius. So this is the total heat gain. Okay. Now, according to the principle of calorimetry, the heat lost by the aluminium sphere will be the same as the heat gained by the water and copper calorimeter combination. Okay, so that implies 0.047 into specific heat of the aluminium into 77 MC delta T relationship for the aluminium sphere heat loss is equal to this much, 0.25 into 4.18 into 10 to the power 3 plus 0.14 into 0.386 into 10 to the power 3 into 3. That implies specific heat of aluminium is equal to this 0.047 into 77, it will come in the denominator here. Okay, 0.047 into 77. Okay, here. So the specific heat of aluminium, it is coming around 0.911 into 10 to the power 3 joule per kg per Kelvin, or we can write it as 911 joule per kg per Kelvin, or we can write it as 0.911 kilojoule per kg per Kelvin. This is the result. This is the specific heat of the aluminium sphere which we had to calculate. Okay, so this is the thing. So this is the very important concept to remember here, that an increase or decrease of temperature, a margin of increase or decrease of temperature in both Celsius and Kelvin scales, they are the same. That is, an increase or decrease of temperature in Celsius scale by a certain margin will lead to an increase or decrease of temperature in Kelvin scale by the same margin. The numerical margin will stay the same, but the units, it will be different. Okay, this is the thing.